For part B, we've been asked to show that there is some point P that has an x-coordinate of 3 at which the line tangent to the curve is horizontal. So that right there should be telling you horizontal tangent, m equals 0, because that's horizontal. So that means this slope, which is equal to m, dy dx is always m, will be equal to 0. And so the important part is when the numerator is equal to 0. So I'll rewrite 3y minus 2x must be equal to 0. Because 0 over 10, 0 over 100, doesn't matter what, these will always be 0. So all we care about is the numerator. They've also told us show that the x-coordinate is 3. So we're going to plug that in. We'll say 3y minus 2x, where x is 3, must equal 0. So that means 3y minus 6 equals 0, or 3y equals 6, y equals 2. So we've found the y-coordinate of the point P. But we haven't necessarily shown that this line will be tangent to the curve, because we'd have to prove that the line, that point is actually on the curve. So we think that this is happening when x equals 3 and y equals 2. But in order to show that this actually is on the curve, we know it's tangent because it satisfies our derivative equation, but we don't know that it's on the curve, so we have to prove that. We've been given x squared plus 4y squared equals 7 plus 3xy. To satisfy this curve, we're going to show that when this is 3 plus 4 times 2 squared, this must equal 7 plus 3 times 2. If both sides are equal, then we know the point is on the curve, and therefore we've satisfied the problem. So we've got 9 plus 4 times 4 is 16. Is that equal to 7 plus 18? Sure enough, 25 equals 25, so we've shown m equals 0. We found y equals 3, and we know that it's tangent to the curve because we used the slope m, and we showed that 3, 2 was on the curve.